Cleaning data. What is cleaning data?
But just because we've got data doesn't mean we've got knowledge. Now, this is going to be a kind of iterative process. We're going to need to clean up our data to make it as useful as possible. We're going to need to transform it so that we can combine data sets together and statistically measure our data sets. And then we're going to need to reduce it sometimes if our data set is too big and unmanageable. And this combination of cleaning data and transforming data and reducing data is a kind of cycle where we're going to iterate this until our data set is the smallest, most useful form it can be. Right? So if we've got redundant variables which are basically the same as others, or we've got duplicates, these are all problems that we need to sort out. Right? Because if we're going to be analysing data with these kinds of issues, we're just making our life slightly more difficult, it's computationally inefficient, and in the worst case, we could draw the wrong conclusion.
This process of cleaning data is important. About 80% of all data projects consist of cleaning data, so it's unavoidably a big part of the job. Characteristics of a clean data set include consistency. That's when observations are always entered in the same way. If, for example, I'm enumerating trees in an urban park, I can't begin by listing ash trees by tree, but then decide midway through that I'm going to exclude all those infected by the emerald ash borer, just because I found out the ash borer midway through and decided that the infected trees most likely won't be there in 5 years. I have to decide from the outset whether or not I'm going to include ash trees infected by emerald ash borer, why I decide to include them or exclude them, and then from the outset I have to be mindful to identify every infected tree and include or exclude them as per my rule. The next characteristic would be completeness. This just means that the dataset needs to be properly filled out. Again, in the case of enumerating trees in urban parks, I can't just decide to exclude a corner of Anquignon Park just because there's a creep in that quarter and I don't feel like going there. The next characteristic is usability. How machine readable is your dataset? Remember how we discussed that there are different ways to store data and some are better than others. We can have a nice, properly formatted CSV file, or we can put out a PDF file whose data is really hard to extract and manipulate with anything. Atomicity is a bit more complicated. It refers to when you have a data change, which affects multiple datasets. Do all the related datasets change properly, or does one change but not the other? When data changes, all affected datasets need to change, or if one doesn't work for whatever reason, all need to not change. A concrete example of this is the following. Think of a money transfer from bank account A to account B. If it consists of two operations, withdrawing money from account A and saving it to account B, performing these operations in an atomic transaction ensures that the database remains in a consistent state. That is, the money is neither debited nor credited if either of those two operations fail. This is a good example if this has ever happened to you. I once transferred a few $1,000s from my personal account to my joint household account. The money got debited from my personal account, but did not get credited into my household account. It was a royal pain in the ass, and it took months to sort out. This is a good example of how sadly my transaction wasn't atomic, and the datasets weren't atomic. This totally stressed me out. A final note is that metadata is important too. What's metadata? Metadata is the data about the data, so it means that we need to be crystal clear on what each column header means. Do we really know what we're measuring? If there are blanks or zeros, what do these mean? Does the blank mean we don't have data, or does the blank mean there's no quantity of something? Or is it data intentionally left out? The metadata is very important. It can actually be surprisingly difficult to precisely define variables. What's being measured, the columns of your dataset, and observations, incidences, or members of your sample, the rows of your dataset. We'll get back to metadata in a future clip. For now, we'll focus on completeness.
conclusions. You might be surprised and disappointed when you get your first data set that actually it's not quite as nice as you were hoping, right? It's going to need some cleaning up. Right? Maybe there's missing values, maybe there's outliers that need to be dealt with because they're warping your distributions and your medians and means, right? And perhaps you also got noise in your data set, right? These few things we can start to address with cleaning. So cleaning data is essentially the idea of trying to correct or fill in any missing values or remove those bits completely. You might be surprised that there's missing data at all. Right? I mean, are we not paying attention? Like, we've got one job and that was to collect the data and we seem to have got missing data. But actually it's quite common, right? Because, I mean, for example, if you're trying to track patient records over time, maybe they didn't show up to an appointment. Or maybe you're in a hospital and they weren't there when they needed to have their temperature taken, right? And then your trend line of your temperature over time is going to be missing some values, right? Maybe you've got data going back for hundreds of years and they didn't have certain techniques and certain measurement systems back then, so they only have other kinds of data. So missing data is very common, right? And we're going to have to be able to deal with it.
So the next question is, how do data scientists analyze data sets to understand what data is missing, and what do they do to solve the issue?
So missing data is very common, right? And we're going to have to be able to deal with it. So the data set we're looking at today is a kind of ratings for chocolate bars. This is why I ate my chocolate, or at least that's what I'm telling myself. So we'll read the data in. We've got 10 different variables. We've got about 1,700 nearly observations. And let's have a quick look using the summary. So we've got things.
Okay, so just to be clear, we're going to see how this data scientist uses his program to deal with these issues. You're not going to need to learn how to do that for this course, so don't sweat too much.
Like the company that produced the chocolate, the name of the chocolate, reviews, the cocoa percentage, the type of bean, this kind of information. Right? And you can imagine what you might do if you were trying to produce better chocolate is to look at a huge amount of this kind of data and work out what it is that customers like and what it is they don't like. Right? This is going to be quite common in market research. So the first thing we're going to do, right, we've received this data, we know now what the columns are, but we don't really know anything else other than this. So we're going to have to start looking through and seeing, first of all, is there any missing data? So we're going to use the sapply function for this. The sapply function will apply a function over our data set. So for each column or each attribute of our data, we're going to apply this, and the function we're going to use, we're writing ourselves. So it's going to be the sum for any time where our item is either blank or NA. Now blank means an empty string, and NA means literally not applicable, right, which is something that comes up in data from time to time. Right, so in any case, both of these are missing values, so we're going to treat them both the same. So if we apply this to our chocolate data set, then we're going to see that, for example, there are 8 missing names, there are 7 missing review dates, and there are 4 missing cocoa percentages. So for each row in our data, there are 4 rows where the cocoa percent is missing. Now that's not too bad. I mean, this is a data set of nearly 1,700 items. 4 is not too bad. That's quite expected. You might imagine that if you're pooling this data from lots of different sources, people are going to forget to add data in, or they weren't able to record data on that day. There's a huge amount of reasons why you might have missing data. And now it starts to become a little bit of a problem when we look at things like bean type, because bean type has got 1,200 missing values. That's a huge proportion of the data set. And in that case, we might have to do something about this. So the only issue we've got is that 1,200 is not relative, it's just an amount of rows. It's not relative to the size of a data set. So we're going to use the exact same function, any empty rows, but this time we're going to divide by the total number of rows. So we can get a percentage for how much of the missing data we've got. So we can see, for example, that company name has 0 missing data, whereas bean type has 74% missing data. So that's a huge problem. Now, a kind of general rule of thumb is if you've got over half your data is missing, it's going to be quite hard to estimate or guess what that data is going to be. That's when you might want to start thinking about removing it. So what we want to do is we want to extract any of the names of any of our attributes that have this sort of over, let's say, 60% missing. Right? So we're going to start by calculating all those percentages and saving them in a variable, and then we're going to select only those percentages where the value is over 0.6, right, or 60%. So we're going to say any attribute where the attribute is over 0.6. And that is just bean type at 0.74, right, or 74%. So we can now delete bean type ourselves. So we could say something like choco, all the rows for bean type is null. Right? And by setting that to null, that's just going to delete that column. We could also do it automatically. So we could actually pass in those attributes that we just calculated as a parameter. So that would be this line here. So it would be something like Choco, all rows, that's here, the names of any attributes where the percentage missing is greater than 0.6. Right? And that's going to just delete bean type. Right? There's not a lot we can do about bean type. We've only got 25%-ish of the data. It's not enough to start guessing what bean types are going to be in other chocolate bars. Let's have a look at now our rows of data. Right? So for each instance, they're going to have a number of attributes. Now there's 9 left. And we want really to keep the instances that have the majority of their data. Right, so we're going to apply, right, so this is going to be row-wise, to dimension 1, so that's the rows. We're going to count any that are blank or NA for each row over our data set, and we're going to put this into missing. So what this is going to do is return a list of values for every single row that tells you how many missing items are there in that row. And so we can now look at the first few missing items. So we're going to order them, right, by largest first, and then we're going to show just the first few, and you can see that actually some of them are missing 7 and 6 attributes. That's quite a serious situation, because there is only 9, right? So they've only got a couple of entries in their fields. Now let's do this again as a percentage of the number of attributes. So this is exactly the same thing, but this time we're dividing by the number of columns, which is 9, and we're going to have a look at the top of these. And so you can see that we're missing 77% of some of these initial attributes. That's a real problem. Missing is the same length as the number of rows we've got. So we can actually look up any rows where there's a greater percentage of missing values than we want and just remove them from the data set. So what we're going to do that is a bit like this. We're going to say Choco is Choco anywhere where missing is less than 0.7 and then all the columns. And what that's going to do is select only the rows we want where they've got a nice amount of data. So the Choco data set is going to be a little bit smaller now, but much more useful to us. We don't really want to be trying to do things like machine learning or statistics when 70% of some of the data is missing. Right? That isn't going to be a good idea. So it's quite easy just to delete data. Right? I mean, in some sense, it's just more convenient to do that. In general, the rule is that if you've got more than 50 or 60% missing data, it's a good idea to delete it. Right? Delete either the instances or the attributes, depending on how much data you've got missing and where. Right? If you're missing a huge amount of data, then you're not going to be able to recreate it by, let's say, using an average. Right? We've got so little data that an average isn't going to be reliable. If we have got sufficient data that we could maybe start to infer what these missing values might be, we can start to try and replace them instead of deleting them. So what we might do is we might, for example, set them all to 0. Maybe if an attribute is missing, we can say, well, okay, if it's missing, we'll just not use it and we'll say it's 0. Now, whether you do that is going to depend on what the attribute is. Some things, 0 is not a useful property, right? And we'll look at that in the chocolate data set in a moment. What we might also do is we might start to add the data set mean into those attributes. So maybe we don't know what the rating for this chocolate bar is, but we can guess that it's going to be around the average rating for any chocolate bar. Again, this is going to depend on your situation, right? You're still making up data in some sense. You've got to be very careful about what you do here.
So let's look at how it plays out when you're just missing certain values and you want to keep either the attributes or the columns.
So we've deleted as much of our chocolate data as we feel comfortable doing. Now let's see if we can fill in some of the missing values with appropriate replacements. So let's have a look at our attributes. Right, so we've got company, name, reference, things like this. Bean type has been removed, but we've still got things like the bean origin and the ratings, and there's a few of these missing from our data set. Can we estimate these rather than completely removing them from the data set? Obviously, the less data you use, the less useful things like machine learning are going to be. So let's look at an attribute and see what we can do. So if we look at bar price, right, that's the price of each chocolate bar, we can see that there's a few missing values, somewhere around 3%. Right, that's something we want to deal with, but we've got enough data, 97%, maybe we can start to guess what the prices of these chocolate bars might be. Right? Now, this is a good instance of a time when you wouldn't want to just populate with zeros. Right? No chocolate bar is free, I wish, and so what we need to do is produce a reliable value to represent an unknown price, rather than just setting them all to be 0. So what we could do here is something like this. We could set every So what we could do here is something like this. We could set every missing bar price to be the average of all the chocolate bar prices. And that way, at least we're not warping our distribution up or down. We're keeping it exactly the same. We're going to say, for the chocolate data set, for any row where bar price is NA, and for all columns, we're going to set the bar price to be the mean of all bar prices, right? And we're going to obviously remove any NAs from that calculation, otherwise it's not going to work. Right? And that's already worked. So now, if we recalculate our missing values, you'll see that bar price now has 0 missing values. So we've fixed that problem. Great. So that was quite an easy one, right? Bar price seems to me to be quite an intuitive time when you just calculate an average and put it in, right? Now, actually, maybe not, because, you know, bar price might depend on where in the world we're selling it, or, you know, what company is producing a chocolate bar. So could we do the same thing for rating? If we take the sum of all the NA values in rating, it's 8. Right, so there are 8 chocolate bars for which there is no rating. So what we can do is we could do something called a stratified replacement. We could say, well, let's group our chocolate bars by country or by company, calculate those averages, and then we can specifically fill in companies' missing ratings based on what that company actually shows in the market, rather than just an average over everything. So what we're going to do is we're going to calculate an aggregate function over of the ratings by company, and we're going to calculate a median. Median is a little bit more robust to outliers. So maybe you make up the very, very expensive or very, very cheap line. The median will get what middle value is. Right? So this is going to be per company, and we can set the columns to be a little bit more helpful using col names. And so now our per company, if we look at it, is each company and the median rating of chocolate bar from, I think, 1 to 5, which I think this data set is going. So now we know that data per company, we can actually fill those in. Now you could automate this process, but we don't have much missing data, so let's just show an example of doing it by hand. So this is the line of code we're going to do, and I'll talk through it. So we're going to say for the chocolate data set, for any value where the chocolate rating is NA, so missing, right, and the company is Vicuna, we want to set the rating to be equal to the Vicuna entry in our new per company average, or median. Right, and that's going to fill in that value there. So we do this for all the missing companies, and what we're going to find is that we've replaced all our missing values with appropriate medians for those ratings per company.
So after that, the next question becomes, what happens with the values that seem like they don't make sense? This refers back to the principle of consistency. When values seem really outside the norm, this raises concerns that there was a mistake in the data entry or the data collection.
So the last thing we might find in our data, right, is outliers. So let's imagine we do a box plot of cocoa percentage. Right? So I'm going to produce a box plot of the cocoa percentage. Now, maybe our assumption is that cocoa percentage in some way informs what the rating is going to be, because maybe a higher cocoa percentage tastes nicer. I don't really know about chocolate. So if we look at this box plot, what we'll see is we've got actually quite a tight distribution of cocoa percentage, right, between about 50% and just above 80%. But you can see there are 3 outliers. When it produces a box plot, I will show outliers as anything that is more than 3 standard deviations away from the median. What we do with these outliers is going to be a judgment call. It's going to depend on the situation. So, for example, we have an outlier here which is above 100%. Now, that makes no sense. We can't have a chocolate bar with more than 100% cocoa, right? It doesn't make sense. So that is obviously a mistake. We would delete that item, right? And probably delete the whole row or re-estimate that value based on a sort of stratified average or a different average. For these lower ones, this is a judgment call. One is just above 20 and one is close to 30%. I don't know whether those are outliers or not, right? Is it possible to make a viable chocolate bar with 20% cocoa? I mean, it may be, right? You're going to have to know a little bit something about the situation that your data was collected in and whether that's reasonable. So you might, for example, delete the bottom one as a mistake, but keep the top one because that's just a low amount of cocoa.
So this is the end of the introduction part 1 to data cleaning. And after this, we're going to get into, okay, what happens when the entire data set is badly organized? What makes a well-organized data set? That is the next clip. Bye.